and I'm a mathematics teacher at the American School Foundation of Monterrey in Monterrey, Mexico. Today, I'm going to be giving you about a 1-hour lecture on the introduction to parametric equations. This is intended for students who have never had any experience whatsoever with parametric equations in the past, and this is an introductory kind of a beginning lesson into this field. So up until now, almost everything you've seen in terms of functions have followed one of two forms. Either y is a function of x, or x is a function of y. And the problem is that we find that some curves don't fit very well into either of those forms. One of the ways that we deal with that is by introducing a concept called parametric equations, wherein instead of defining y in terms of x, or x in terms of y, we define both x and y in terms of a third variable called a parameter. It usually looks something like this, where we have x as a function of t and y as a function of t. The third variable, t, is often time, and sometimes it's helpful to think of it that way, but it certainly doesn't have to be time. It could be an angle, for example. We could have x equals f of theta, y equals f of theta, or any one of a number of other things. When we let t, in this case, vary from all of the points on its domain, and graph those points in a Cartesian plane, we get a graph that's called the parametric curve. You've actually already had some experience with parametric equations, perhaps without realizing it. In physics class, you would have studied projectile motion. And in projectile motion, if you remember back to your physics classes, you'll remember that there are two kinds of motion that we deal with. We have motion in the horizontal plane, often called the x-plane, and we have motion in the vertical plane, often called the y-plane. And you'll remember that the motion in one plane is independent of the other, in that what's happening in the x-plane doesn't affect what's happening in the y-plane and vice versa. And we usually have a series of equations for the motion in the y-plane, and usually one equation for the motion in the x-plane. That equation is x equals v times t, because there's no acceleration in the x-plane. And we solve those equations to determine various aspects of the projectile, its height at a certain time, or its distance traveled, or how long it takes until it lands, or what is its maximum height, things of that nature. And those are all examples of parametric equations. So let's start by taking an example. In this example, we're asked to sketch the parametric curve for the parametric equations x equals t squared plus t and y equals 2t minus 1. So what that means is we're going to graph a series of coordinates of xy points, just like always. The only difference is now x is determined by the equation t squared plus t, and the y coordinate is given by 2t minus 1. So for example, if t equals 0, we find that the x-coordinate would be 0 plus 0, which is 0, and the y-coordinate would be 0 minus 1, is negative 1, and so we know that the coordinate 0, negative 1 is 1 point on our curve. And we could continue to build a table of values to plot the curve in this way, and in fact that's not a bad way to do it. So if we go to fill in this table of values, we would be able to take those points, plot them, and perhaps determine the nature of the curve. I'm going to ask you to pause the video right now for a few minutes and fill out this table of values and then sketch the curve. Okay, hopefully you're finished with that now. So let's see if your answers agree with mine. So when t is negative 2, we find that the x-coordinate is 2 and the y-coordinate is negative 5. How do we get that? We put a negative 2 in for x, and we get negative 2 squared is 4, plus 2 is 2. Sorry, minus 2 is 2. And we put a negative 2 in for t here, and we get 2 times negative 2 is negative 4, minus 1 is negative 5, and so we have the point 2 minus 5. Similarly, we let t equals negative 1, and we find that x is 0, and that y is negative 3. If we let t equal minus a half, we find that the x-coordinate is minus 1/4, the y-coordinate is negative 2. If we let t equal 1, we already found out that that's the point 0, negative 1. And when t equals 1, we have that x is 2 and y is 1. And now that we've got those 5 points, we could plot them on an xy plane and perhaps we could figure out what the equation looks like. When I did that, I plotted the point at t equals -2, and then -1, -0.5, 0, and 1, and we can see that this appears to form a parabola opening horizontally. And because time is going from -2 to +1, this parabola actually has a direction. It moves from the bottom branch over towards the vertex, and then back along the top branch off to infinity. So now there's a couple of things that you might be wondering about how we did this. One question that I hope you have is, how do we know what values of t to choose? In other words, why did we choose -2, -1, and especially why did we choose -1/2? That seems like an unusual choice. So how did we know to pick those values? Because as you can see, the point -1/2 was particularly important because it turned out to be the vertex of this. How do we know how to choose those? Well, we got lucky. No, we didn't really get lucky. I had already worked the problem out a different way, and I knew that the vertex was going to occur at t equals -1/2. But if you just started with a table of values, you wouldn't know that. So what's our conclusion? Our conclusion is that a table of values, while quite easy to do and quite useful for getting an idea of what's going on, is maybe not a very great choice for sketching parametric equations. Now, sometimes we don't have any other choice, but when we do have another choice, we tend to avoid this method. I should also point out that sometimes there will be limits on the parameter. Okay, so let's consider this revised version of the same problem. Notice here we're asked to sketch the parametric curve for the parametric equations x equals t squared plus t and y equals 2t minus 1. That's exactly the same question we just had, except now t is only going between -1 and +1. So this set of values up here would no longer be considered. All of these would. And how does that affect our curve? Well, now we only see a part of the parabola. We're only starting at -1. So that means we're starting at this point right here. So my parabola now looks like this. It has a well-defined starting point and a well-defined ending point. Notice there's still a direction involved here. We're still going from -1 to -0.5 to 0 to 1. But now, only a part of the curve is going to be allowed. Well, now I said that a table of values is not a great way of doing this, so it's left to us to figure out what is a better way of doing it. So let's look at, again, the same question. This time we don't want to do it with a table of values, and so we do something called eliminating the parameter. Remember, the parameter is what we call t. T is the parameter, so we'd like to eliminate that. The way we do that is by recognizing that the easiest of these two equations to solve for would be the y equation. And we get y equals 2t minus 1. Now, if I want to isolate t, that's quite easy to do. I move the 1 to the other side, I divide both sides by 2, and I'm left with t equals a half of quantity y plus 1. And now that I know what t is, I could take this t value and substitute it in for x, and I would then have an equation involving x and y. So instead of x equals t squared plus t, I now have x equals this t value, a half y plus 1 squared, plus a half y plus 1. And if I do a little work with that, I expand it, and I get that. I multiply the 1/4 through the brackets. I get that. And now I recognize, well, I might quadruple both sides to get rid of these fractions. And I look at that and I recognize that that is the equation of a horizontally oriented parabola, something that we dealt with in our study of conic sections. So we could rewrite this in vertex form by completing the square on the y squared plus 4y. So this becomes y plus 2 squared minus 1. We bring the 1 over and we simplify this down, and we're left with y plus 2 squared equals 4 times x plus 1/4. And we recognize that as the standard equation of a horizontally oriented parabola with a vertex at -1/4 minus 2 and opening to the right. And we can graph that, and if we graph that, we're going to see the exact same equation that we had in the previous example, but we didn't have to rely on guessing which points were important and plotting tables of values, which can get really tedious. Now, this is a better approach because of those reasons, but there are still a couple of problems with this approach. Number one, as soon as we eliminate the parameter, we're left with this equation, y plus 2 squared equals 4x plus 1/4. But remember what we said before. We said that in parametric equations, the curve has a well-defined direction. And looking at this Cartesian equation, we have no way of knowing what the direction is. So eliminating the direction does not allow us to determine the direction of motion. Eliminating the parameter, rather, does not allow us to determine the direction of motion. And sometimes, not in this case, but in sometimes, eliminating the parameter gives us an equation that's even harder to graph than the original parametric equations. Now the first problem we can still solve just by plugging in a few values of t and figuring out the direction. The second problem is sometimes more challenging, but very often we can deal with that by making smart substitutions, as in the example we're about to do. So in example 2, we're asked to sketch the parametric curve for the following parametric equations and indicate the direction of motion. And we're told that x equals 5 times the cosine of t and y equals 2 times the sine of t, where t is allowed to go from 0 through 2 pi. So how do we do this? Well, we could try and do exactly what we did in the last example. We could solve, for example, x equals 5 cosine t. We could solve that for t. And if we do that, we find that t equals the inverse cosine of x over 5. So far, so good. And now we could take that and plug it into t in my y equation, and then I would have a Cartesian equation. Namely, I would have y equals 2 times the sine of 5 cosine inverse of t. Well, this is good. It's a traditional function. Okay? We have y in the terms of x. Problem is, we have no idea how to graph this. This is even harder to graph than these would have been. And so, in this case, eliminating the parameter didn't seem to help us very much. Now, we could go back to a table of values, but we've already talked about what some of the problems are with that. So instead, we try to see if there's a clever way that we can use trigonometric identities to help us with this. Now, of all of the trigonometric identities, your favorite, I'm sure, is the Pythagorean identity. In other words, sine squared plus cos squared equals 1. So we'd like to try and use that if we can. So what we do is we solve our x and our y for sine and cosine. So we have x equals 5 cosine t, which means that cosine t equals x over 5. And we have y equals 2 sine t, which means that sine t equals y over 2. Now if I square these and add them, I'll get cos squared plus sine squared, which is 1, equals x over 5 squared plus y over 2 squared. And so that leaves me with this. Now I have a Cartesian equation, but a much nicer looking Cartesian equation than this one we had up here. This, I'm hoping, you'll recognize as an ellipse. If we expand this out, we're left with x squared over 25 plus y squared over 4 equals 1. And that, of course, is a horizontally oriented ellipse, centered at the origin. Major axis is 10, minor axis is 4. And so we're centered at 0. We go plus or minus 5 in the x direction from 0. We go plus or minus 2 in the y direction from 0. And we're left with this ellipse, which is quite easy to graph and quite easy to see. Now, as we said before, we've eliminated the direction of motion. This ellipse has a direction, and we need to figure out what it is. And so, in order to figure out the direction, well, now we can go back to a table of values. So again, I'm going to ask you to just pause the video, fill out this table of values, and then try and sketch the graph. I'll give you a minute to do that. Okay, so let's check and see whether your answers agree with mine. When I worked out these values, when t equals 0, I got that x was 5 and y was 0. How did I pick these values of t? I chose easy values that are going to go into my trig function. So in other words, I chose pi over 2 intervals all the way along here because I know that it's very easy to plug in 0, pi over 2, pi, 3 pi over 2. Those numbers go into sine and cosine very nicely. At pi over 2, my x-coordinate turned out to be 0. My y-coordinate turned out to be 2. At pi, we have an x value of -5 and a y value of 0. At 3 pi over 2, we have an x value of 0 and a y value of -2. And at 2 pi, we're back to where we started with an x-coordinate of 5 and a y-coordinate of 0. If we plot those on a Cartesian plane, we get this ellipse that we had already seen, but now we can see the direction. We can see that this starts at the point 5, 0, and it goes anti-clockwise 1 lap back around to 5, 0. And that's only going to give us one complete ellipse because t is allowed to vary only from 0 to 2 pi. Now, what if we modify this previous example just a little? So you'll see this is the same question we had before, except instead of 5 cos t and 2 sine t, we now have 5 cos 3t and 2 sine 3t. T is still allowed to go from 0 to 2 pi. Well, just like in the last case, we can isolate our cosine 3t and our sine of 3t. We can square those, and cos squared 3t plus sine squared 3t still equals 1. We get exactly the same equation we just had. X squared over 25 plus y squared over 4 equals 1. It's exactly the same ellipse we just had. The difference is, now, this function, this y function, and this x function, instead of having a period of 2 pi, have a period of 2 pi over 3. In other words, we've had a period adjustment. The 3 in front of the t gives us a horizontal compression. In other words, we get 3 times as many periods in the same amount of t. And so now, what we have is the exact same ellipse we had before, except it's going to go around 3 times. So we get 3 laps of the same ellipse. If we just look at the graph, it's going to look exactly the same. But if we actually were to plot it out, we would see that we'd start here, we'd go all the way around once, we'd go around again, and we'd go around a third time when t goes from 0 to 2 pi. Let's look at another example. In this example, we're told to sketch the curve for the following set of parametric equations and to indicate the direction of motion. We're also asked that if the curve is traced out more than once, to give a range for the parameter for which the curve will be traced out exactly once. Our curve is given by the parametric equations x equals sine squared of t and y equals 2 cosine t. So if we follow the same process as before, we could get the cosine by itself. So we would get y over 2 equals cosine t. We've already got sine squared. And so this is going to give us x plus y over 2 squared would equal sine squared plus cos squared, which is 1. So we get x plus y squared over 4 equals 1. And we recognize that, again, as a horizontally oriented parabola. We put it in standard form, and we got y squared equals -4 times x minus 1, which is a parabola, horizontally oriented. The vertex is at 1, 0, and it's opening to the left, as indicated by this negative in front of the 4. We have to be a little careful here, though, because this is not going to be a parabola extending off to infinity. Why not? Because x and y are defined in terms of sine and cosine. And sine and cosine have limited ranges. For example, we know that the cosine curve oscillates between positive and -1. When we double that, we can see that y is therefore going to go no higher than 2 and no lower than -2. Likewise, sine goes between plus and -1. So sine squared goes between 0 and 1, which means that x is never going to be any bigger than 1 and never going to be any smaller than 0. So now when we go to graph our function, we have to recognize that. We have to understand that x is only going to be between 0 and 1 and y is only going to be between -2 and +2. So again, we're going to get a parabola, but we're only going to get a piece of a parabola. And we see that we get this chunk of the parabola. T is going from where to where? Well, we don't actually know. We're asked to figure out how far t can go. So let's try a few points. When I let t equal 0, I get the point 0, 2. So this is where I start. I try pi over 2 because it seems like a good number to try out. And at pi over 2, I get the point 1, 0. When I put pi into these functions, I get the point 0, -2. And if I go farther than that, I realize that at this point, the parabola turns around and it comes back the same direction again, and it will just keep going back and forth like this. So the question asked us to determine a range for the parameter that will trace out the curve exactly once, and it turns out that the curve is traced out once when t goes from 0 to pi. So we've been talking about graphing parametrically defined parametric equations. In other words, if I have a curve that's defined parametrically, how do I graph it? Now sometimes it's useful to go the other way. In other words, if we've got a function, can we come up with a parametric curve that describes it? That's called parameterizing the curve. And for the purposes of this course, the only type of thing that we're going to look at here are lines, okay, which is the easiest kind. So let's try and find parametric equations for the line going through the point 3, -1 and with a slope of 4. So if I sketch that situation, I get something that looks like this. Okay, there's my point 3, -1. My line has a slope of 4, which means every time I go over 1, I go up 4. So for example, I can see that I'm going to also hit the point 4, 3. If I go over another one, I go up another 4, so I'm also going to hit the point 5, 7, and so on and so on. How do I get the parametric equations? Well, I start by just making something up for x. I say, let's let x equal 3, because that's where it starts. It starts at 3. And then just say 3 plus t. In other words, as time gets bigger, x gets bigger according to 3 plus t. When t equals 1, x is going to be 4. When t equals 2, x is going to be 5. When t equals 3, x is going to be 6, and so on and so on. And because the slope is 4, I recognize that every time I go over 1, I have to go up 4. So therefore, when t is 1, y has to go from -1 up to +3. It has to go up 4. And so therefore, I now know what my y coordinate must be. My y value, my y parametric equation, must be -1 because that's where it starts, plus 4t. Why 4t? Because every time t goes up by 1, my y coordinate has to go up by 4 because the slope of the curve is 4. We find that in order to parameterize a line, we really only need two things, the same two things we need to graph a line. We need a point and a slope. And in general, if you want to memorize a form, which I don't really think you need to do, I think probably just applying this process that we did here in example 5 is the easiest way to do this. But if you're someone who likes to memorize processes, you can just remember that in general, if I have a line going through the point A, B with slope r over s, then it's parameterized by the parametric equations x equals a plus st and y equals b plus rt, where t is allowed to go from -infinity to infinity unless we're told otherwise. So that's our introduction to parametric equations. I hope that this has helped. For homework, I'm going to assign handout 2, which will be posted on my Google Drive file in the next little while. And I'm going to encourage my students to go through handout 2 and be prepared to discuss those in our next class. Thank you.